Okay, welcome. Here I'm going to try to prove, at least to some detail, how we find the so-called sampling distribution of the sample variance, funny enough. That is, when we compute a variance based on some numbers and we consider it as, let me give you the formula here. When we compute a sample variance, here I express it in terms of random variables because this is how we need to consider it to realize that a sample variance itself is a random thing, that from sample to sample, a sample variance will change. So in a new sample, the sample variance will have a new value, and that is to say that the sample variance has a sampling distribution. It distributes itself from time to time. The question is, what is the sampling distribution of such a sample variance? How does it change from time to time? Can we actually find that? Well, the claim is, and we've used it already in the course, the claim is, which we will give a level of proof, that at least if we assume that the variables that enter the computation, the random variables, actually are normal and independent, the usual assumption. If we assume that, we have used in the course already that if we take the sample variance and multiply it by n-1 relative to the true underlying variance sigma, then this statistic is actually chi-squared distributed with n-1 degrees of freedom. That is basically the claim that, or the theorem we could also call it, that we are going to make a proof of. Now, we are going to use some of the moment generating function stuff to actually prove this. We're going to use different things that I have gone through in previous videos. But there is like a kind of an indirect way to the result here. Actually, we will first look at the sum of such xi's, we'll do so, instead of directly going for the variance as it comes, the sample variance, I look at something sort of more theoretical, you could say, where I take each random x relative not to the mean of the x's, but to the underlying mu over sigma squared. This is the first one, and then we will get to the result at the end, actually. The thing is, if I look at this, I can see different things. I can see that this is actually set I squared, where set I is standard normal. Because when xi is normal with mu sigma squared, then set I, which is the standardized one, we've used that also previously using simple rules, then that is also a normal, but now a standard normal. So we have that this sum equals a sum of squared standard normals. Well, we have proven in a previous video that having a single squared normal becomes a chi-square 1, right? Having a standard normal and squaring it gives a chi-square 1. That is a thing I've proved previously, actually. I have also proved that when I take the sum of independent chi-squares, when I take the sum of independent chi-squares, I did that in a video on sums of random variables, I get something which is chi-square distributed with the sum of degrees of freedom. And now I have n terms, each of them has a degree of freedom of 1. I sum it up to become n. So using results from previous videos, I have this statement. This is not enough for me, but that's a start. I have the statement, so if I take this theoretical term, it follows a chi-square n distribution. Now the trick comes that I use this theoretical term and sort of identify what I'm actually interested in by the following trick. I say this equals something else. Let me do it in detail here. What I do here is a little trick that I subtract and add the mean of x here, the average of the x. So basically, I add and subtract the same thing, which means that altogether the whole thing has not changed. But I do this for a reason. I do it for the reason that now I can split up and take the first part squared and the second part squared. Here, I equal 1 to n. I take the first part squared, like this. And note that this is very close to what I'm actually interested in. Then I take the second part squared, like this. Then actually, this is the square of a two-itemed thing here. So I should actually have the double product here. I should have twice the product of the two things, like this. But I will not write it here in more detail, because and this is where I skip some details. If you look at this term, you will realize that this term actually vanishes. So this becomes a zero term. Things simple cancel out in this term. So we are left with this part here, meaning that now we have a look at this one actually. Let me rewrite this one here. I expressed this one now. And actually, here I have the one that I'm interested in, almost, I should say. Let me see how to phrase it. Maybe I should put it like this, that here I have actually n minus 1 times s squared over sigma squared, like this. Let me see. Because when I compute the variance, I divide by n minus 1 here. So if I write the variance times n minus 1, this is what I have. So basically, apart from the scaling term n minus 1, this is what I was interested in. Then the second part, let's have a look at that. I'd like to rewrite that a little bit. Please note the second part here. It doesn't actually depend on n. It doesn't depend on n. So it's the sum of n of the same term, so it becomes n times this sum. And instead of writing this n times this sum, I put in the n in here, which is then n times this sum actually. Having done this, I can see that I know this one, actually, because I know that x bar, the average of x, has a normal distribution with mean mu and variance sigma squared over n. This is a well-known fact from previous, which means that, again, this one, in fact, is just a standard normal squared. Again, standard normal squared, which means that this one is, in fact, a chi-square 1. Now I have, you could say, that a chi-square n, you could say, equaling my term, the thing that I'm interested in, plus a chi-square 1. This is kind of symbolic expressing what I've found. Now, to finalize the argument, then I mean the argument is, because this is a chi-square with n, this is it's the sum of two things, which one of them is a chi-square 1. That then means, actually, that my term and my term is n minus 1 s squared over sigma squared, actually is a chi-square n minus 1. That's how it goes. To make this latter argument precise, we would need, again, to make this precise, we would need moment-generating functions, as I introduced previously in a previous video. Because, let me just sketch it here, we would know from moment-generating functions because of this sum and because of the independence between actually x bar and the sample variance is independent. This is some result, of course, you could also prove, but now I just throw it in your face, and you'll have to believe my word here, that the sample variance and the sample mean are actually stochastically independent. So, which means that I can express the moment-generating function of a chi-square n as the product, that's due to the product rule of moment-generating function, as the product of the moment-generating function for the thing that I'm actually interested in times the moment-generating function for a chi-square 1, like this. And then I can solve this to achieve the final result, that I can get the moment-generating function for my thing of interest, my term as I called it before, by having the moment-generating function of the chi-square n t divided by the moment-generating function of the chi-square 1 of t. And these moment-generating functions of the chi-square is actually 1. Sorry about this. 1 minus 2t to minus n half, and 1 minus 2t just to minus half, and altogether that becomes 1 minus 2t to minus n minus 1 half. And then we use the classical argumentation here. I say, aha, I can recognize the moment-generating function for a chi-square with n minus 1 degrees of freedom. So I have now proved the claim that the sampling distribution of, up here it was, the sampling distribution of this thing is chi-square with n minus 1 degrees of freedom. Thank you.